Hello, my name is Kaitlyn and I'm an ASTS math tutor. In this video, I'll be going through how to use the DISC method, which is in section 6.1 for Calculus 2 or Math 141. So chapter 6 is all about applications of the integral, with section 6.1 focusing on volume. One way to approach and solve problems of volumes of solids of revolution is by using the DISC method. So first we'll go over the concept of the DISC in a solid of revolution, then we'll solve a textbook problem step by step. So I'll be solving problem 2 in section 6.1 of the textbook Calculus with Concepts in Calculus by Ellis and Gulick. So first let's go over sort of what a solid of revolution is and how to find the volume using the DISC method. So let's think of f of x, a continuous function from a to b. So here is our f of x from a to b. And the region under the curve from these bounds will be r. So everything under this curve from a to b is r. If we revolve r around the x-axis, so we're revolving around the x-axis, we'll get a 3D solid of revolution. So we're revolving this entire section around the x-axis. So if you can think in 3D, that's great. If not, I really love to draw pictures. So here's an idea of what this revolution, what sort of solid this revolution would create. So here we still have our y equals f of x. We're still in the bounds a to b. Here's sort of that section here, and we end up getting some sort of odd shape like this. So we want to find the volume of the solid we just created through this revolution. So I like to do that by, again, let's look at our section R. Let's redraw this. So we have our y equals f of x from a to b. And let's take a slice, or a disc rather, right? We're doing the disc method. So we're taking this small slice, and since this is from the x-axis to our function, this will be f of x right here. And here we'll have our dx. And I know this looks like it has some sort of large width, but really this is our dx. This could be any size, just some small sliver. And we're going to revolve around the x-axis. So instead of revolving our whole section R, we're going to revolve our disk that we just created. So this is what it would look like somewhat if we revolved this disk. So if we have this section from the x-axis to our y equals f of x, that's a radius, right? This sort of looks like, well, it's a disk, right? It sort of looks like some ovular, roundish, circular-esque shape. So here's our r, and that's going to be f of x. So here we have our f of x, and our dx, also h. So h is dx. And again, using this disk method, instead of trying to find, the whole volume of r when revolved, we're going to find the volume of our disk that we just created. So this volume equation may look familiar, right? Pi r squared h. And we're going to substitute in what we just set up, right? Their r being f of x and our h being dx. So we get the volume of the disk equals pi f of x squared dx. So this is if we revolve some function y equals f of x that's continuous on a to b about the x-axis. So here's our total volume equation, and this is the volume of a disk, so the disk method. So this is the volume of our disk. To find the volume of our region R for the solid revolution, we would just take the integral, right, on our bounds a to b. So this is all to find the volume of a solid of revolution, and this is what we call the disk method. So now that we went over the concept, let's go through a practice problem. So this is from the textbook, section 6.1, problem 2. The problem states, Let R be the region under f of x equals 1 plus x squared on -1 to 2. So we got some important information there, right? F of x equals 1 plus x squared and -1 to 2. Find the volume of the solid of revolution obtained by revolving R around the x-axis. Okay, so most of the time you'll just be given a word problem like this, and you'll be left to your own knowledge of how to solve this, how to get the volume. But a really great place to start if you have trouble thinking in 3D or figuring this all out is to draw a picture. So you see here, I drew a pretty bad picture, but it will help us solve a little bit. So if we have our f of x here, right? Not quite like this, it'd be more like, this. We have some exponential, x squared starting at 1, right? 1 plus x squared on the bounds, -1 to 2. And here is our area under the curve is R. And I also drew our disk. Took out this little disk section here. From x to our function, we have f of x equals 1 plus x squared. And we have our section dx. And revolving about the x-axis. Okay, so the first thing we're going to need to do is we're going to need to write the volume equation. So on the last slide, I had v equals pi f of x squared dx, and that's the volume of the disk. Here we want the volume of the solid of revolution. So the only thing we add to that equation is our integral from bounds a to b. So the problem gave us f of x, and it gave us our bounds. So let's plug that in. So f of x, we're going to plug in 1 plus x squared. A, our lower bound of integration will be -1, and our upper bound of integration will be 2. So here we have v equals integral from -1 to 2 pi 1 plus x squared dx. So we're going to want to expand this term here, right? We have 1 plus x squared. So we're going to want to FOIL this. You may use FOIL, you may use like the box method. I'll just go through it using FOIL. So let's put it up here. First, outer, inner, last. First would be 1 times 1, so that'll give us 1. Outer would be 1 times x squared, which will give us 1x squared. Inner would be 1 times x squared, and that'll give us another 1x squared. So we add those, we get 2x squared. Then last, x squared times x squared, we're going to add the exponents, we get x to the 4th. You may note another thing I did was I took out pi. Took it on the outside of the integral, we're multiplying. It's multiplied by every single term inside the integral. So we can just pull it out. It doesn't have any x's in it. It's just a constant. We'll pull it out and make things simpler. So we can't simplify in any other way. So now, the fun part, we're going to integrate. Lucky for us, we have a really easy integral, right? So we're going to do the integral of each term. So integral of x squared would be x to the 5th over 5. Integral of 2x squared would be 2x to the 3rd over 3. And the integral of 1 is just x. Again, we're multiplying by pi. Every single thing is multiplied by pi. And because we have bounds of integration, we can't forget those. That's a really common mistake. We still have to account for those, and we'll plug them in. So we'll plug in 2 to every single term, and then subtract, and we'll plug in -1. So again, pi times everything. Let's plug in 2. 2 to the 5th over 5 plus 2 times 2 to the 3 over 3 plus 2. Then minus, and we're going to plug in -1. So -1 to the 5th over 5 plus 2 times -1 to the 3rd over 3 minus 1. So let's simplify that a bit. Again, multiply everything by pi. Our 2 to the 5th becomes 32 over 5. 2 times 2 to the 3rd over 3 becomes 16 over 3. So we have our plus 2. Our -1 to the 5th over 5 is just -1 over 5. Our 2 times -1 to the 3rd over 3 is just -2 over 3. And our -1 is still -1. So now we're going to still simplify. A lot of times, common mistakes are with these fractions. It's really easy to drop a negative. So don't forget, negative times a negative. Distribute this negative, we'll get positive. So let's simplify these fractions a bit more. So I just grouped everything with their common denominator because we have 5, 5, 3, 3, and then like 1, 1. So again, everything's still multiplied by pi. Now I group them together. 32 over 5 plus 1 over 5. Again, it turns into a plus because we have negative times a negative. And then plus 16 over 3 plus 2 over 3, and then plus 2 plus 1. Let's just go through. So 32 over 5 plus 1 over 5 gives us 33 over 5. 16 over 3 plus 2 over 3 gives us 18 over 3, which is 6. Then 2 plus 1 gives us 3. Almost done. Let's just put this in terms of 5. Let's add, multiply by pi, and then we'll have our volume. So I did just that. 33 over 5 plus 45 over 5. And then we multiply by pi, add, we get 78 pi over 5. And this is the volume of the solid of revolution obtained by revolving r around the x-axis. To learn more about Chapter 6 or any Math 141 concepts, you can sign up for a session, a tutoring session with me, Kaitlyn, or Cassandra with the ASTS platform. Thank you.